Okay, let us continue. So first, quick announcement. As I said, there will be shuttle buses to take people to the banquet, but for the participants who are staying here and not joining us, there will be a shuttle bus after dinner, the usual time, but maybe just one bus will go through all the hotels, okay? So our next speaker today is Professor Grigori Olshanski, who is joining us online, and who will talk about Macdonald-level extension of beta ensembles and multivariate hypergeometric polynomials. Thank you.
Many thanks for the opportunity to give this talk in memory of Igor. In my talk, I will describe some combinatorial models of random particle systems. The origin of these models is, in fact, representation theory of certain infinite dimensional groups. But I will focus mainly on algebraic and combinatorial aspects of the theory. So this is the brief contents of my talk. This section is about preliminaries, motivations, and all the results. The main results are here, section 2, and the rest is some complements if time permits. So let me fix some basic terminology. So a collection X of endpoints on the real line, I will call it an n-particle configuration. This is my notation for the space of all n-particle configurations on the real line. N-particle ensemble is given by a probability measure M on this space. Given such a measure, we may speak about random configurations. And the problem I will discuss in the case of very concrete models is how to construct ensembles with infinitely many particles. This problem is not trivial because the space of infinitely many particles is very big. And so in general, it's not easy to deal with probability measures in such big spaces. And a possible way to address this problem is to use the so-called large N limit transition, namely to approximate the infinite particle random systems by ensembles with N particle systems as N goes to infinity. So I start with preliminaries. And let me recall what is Dyson circular beta ensemble. So let T be the unit circle in the complex plane, and consider the space of n-particle configurations on the circle. The definition is the same as in the case of real line, namely you have a circle with some collection of points which I call particles. And we are in, this is my notation for the set of probability measure on some space, to be precise. So in particular, I am interested in probability measures on this space, the space of n-particle configurations on the circle. So if you are given such a measure, we may speak of an ensemble of random n-particle configurations. Now let's fix the parameter beta, which is a positive number. And the Dyson definition is as follows. The Dyson circular beta ensemble is given by a probability measure on the space of configurations, and this is this probability measure. The notation is as follows. This is the measure, the natural Lebesgue measure on the torus. And this is the Vandermonde, the modulus of Vandermonde raised to the power beta. And this is some normalizing constant, because the probability measure, we need the mass of a measure to be equal to 1. So this concept is due to Dyson in the early 60s. And the origin of this construction, of this definition, is as follows. Consider three special values, 1, 2, and 4, which actually corresponds to the fields. Sorry, what is here? Oops. Real, complex, and quaternions. And then the Dyson ensemble admits a simple matrix or Lie group interpretation, namely, we consider three infinite series of compact symmetric spaces. This one, unitary group, orthogonal group, the product of two copies of a unitary group and the unitary group embedded here by the diagonal map, and unitary group and compact symplectic group. And next, consider double cosets with respect to the subgroup which I denote by K. And in the case beta, the simplest case, beta equal to 2, the double cosets are essentially the same as conjugation classes in the unitary group. And it turns out that in all three cases, the double cosets can be parameterized in a natural way by configurations of n particles on the circle. So you have a natural projection from our group, this one or this one or this one, to the set of double cosets, which is identified with a space of configurations. And we take the normalized Haar measure on this group and take its push forward under this projection. And what we get is exactly the Dyson measure on the configuration corresponding to these three special values of parameter beta. But for general beta, we just extrapolate in a natural way, just put here an arbitrary number. There are no groups, no symmetric space, but nevertheless, the picture, the definition is the same. Well, so for me, it's interesting to pass to this, I will call it dual picture. Dual picture, what means? It's related to the problem of harmonic analysis on certain infinite dimensional symmetric space. So what means this dual picture? This means that instead of a compact symmetric space, we consider the Hilbert space of functions on the symmetric space with respect to a natural G invariant measure, the push forward of the Haar measure. And in this space, we have a very natural unitary representation of our group, one of these three possible variants on this space. And its decomposition is multiplicity free. It's well known. This is an example of a relatively simple problem of spherical non-commutative harmonic analysis. So what is the question now? The question is, assume that beta is special. So we have some representation, theoretic interpretation of our picture. So the question, is it possible to give a sense to the large n limit of this representation? So we would like to construct some infinite dimensional analog. Infinite dimensional, I mean n, replace n by infinity. We would like to get some unitary representation of some B group, infinite dimensional group, which can be understood, for instance, as an inductive limit or union of a growing chain of finite dimensional Lie groups. And the second question is, assume that it's possible how to decompose these representations into irreducibles. This is the problem of harmonic analysis. Why this question is non-trivial? This is so because on infinite dimensional analog of symmetric space, there is no invariant measure. So we cannot extend our construction directly. There is no naive definition of this L2 space. Nevertheless, one can construct some kind of limit representations, and it turns out that its construction depends, it involves some additional continuous parameters. And this is not a defect of the construction, but in fact, it is a bonus because the picture becomes more rich and more interesting. And next, it turns out that one can decompose these representations into irreducible representations. The spectrum is not discrete, but continuous, actually. And it is governed by a certain ensemble, some particle ensemble with infinitely many particles on the real line. And this ensemble is obtained as a large n limit of certain discrete ensembles on the lattice Z. So the pre-limit ensembles live on the lattice Z, on some discrete object, while the limit object lives on the space of configurations on a continuous space, the real line. And this pre-limit discrete ensembles turns out to be a certain discrete analog of Dyson beta ensemble. And next, it is important that the whole construction admits a purely combinatorial interpretation. And these combinatorial interpretations already makes sense for all beta, not the initial three special values. Thus, we can convert our problem of harmonic analysis for infinite dimensional spaces into a problem, a certain problem of algebraic combinatorials with a slight probabilistic flavor. So let me explain what are these discrete beta ensembles on the lattice Z. It will be convenient for me to assume that beta is an even integer and introduce a new parameter tau. Beta is 2 times tau. It's for sake of simplicity only because the results hold for any positive beta, but the formulation becomes more involved, so I will deal only with this case. The discrete ensembles in question live on the lattice Z, and remark that its lattice Z is dual to the circle. So instead of a continuous space of configurations on the circle, we are now dealing with a countable set of configurations on this lattice. So its elements are n-particle configuration or simply subsets on the lattice of integers. And these objects actually are veiled highest weights or signatures of a unitary group, and the correspondence with the configurations and the signatures, lambdas, is as follows. And here we have this parameter tau involved in this formula. Well, and now I want to define some probability measure on the set of configurations on my lattice. So to do this, I need to define the weight, some weight, probabilistic weight, associated with a given configurations. So this is my configuration of points on Z, and this is the formula. This is the formula. Let me explain the notation. So what is what? So this is a function on my lattice. It is a product of a ratio of products of gamma functions. So L is a point on the lattice. So this is this term. What is this? This term is given by the following expression. This is the Vandermonde raised to power 2, and this is some additional terms. And okay, so what should be noted here? If tau equal to 1, the simplest case, which corresponds to beta equal to 2, then this term disappears. So we have exactly the Vandermonde raised to power 2. If tau is greater than 1, then due to this expression, this term vanishes whenever the distance between the points is too small, less than tau minus 1. This implies that our measure actually lives on a subset of configurations, which I will call tau sparse configurations. Tau sparse means that any two particles must be separated by at least tau minus 1 whole. So we have picture like this. Two particles and some number of holes. For instance, if tau is equal to 2, there is at least one hole between two particles. And if these distances are large enough, becomes large enough, then approximately we get again the Vandermonde raised to the power beta, as in the Dyson case. In this sense, this is an analog of Dyson ensemble. Now I state the result. So let the parameter tau, and these are my additional parameters of a model, are fixed. And after a certain scaling, which is necessary here, and another transformation, I will be sloppy, I'm sorry, these measures converge as n goes to infinity to some probability measure that lives on a certain space of infinite particle configurations on the real line. These are some references. So these are all the results. So this is why I am so sloppy. Now let me pass to the main results, the Macdonald-level construction. First, some notation. So I assume that Q and T are two parameters of Macdonald polynomials. I assume these inequalities. I assume that T is equal to Q raised to power tau, and tau is a positive integer for simplicity only. I need also two additional parameters, a negative number and a positive number. I need them to construct what I call two-sided Q lattice. Its definition is as follows. You see, for instance, if these numbers are equal to -1 and +1, we just have this is positive part of the lattice, or minus. This is the negative part of the lattice. Negative part, positive part. So we have a picture like this. So we see that the lattice nodes are accumulated to 0, which is excluded from our real line, and diverge as we go to plus or minus infinity. And now this is my notation for the set of n particle configurations on this Q lattice, which are tau sparse. Okay, and the next some some notation I need. So this is this infinite product. It's convergent because Q is less than 1. And it is closely related to the notion of Q version of a gamma function, because this Q gamma function is actually the ratio of two products of such a type, some additional, simple additional terms. And the definition. Now, I want to fix some quadruple of parameters which are subject to condition I will specify shortly. The following formula determines a so-called hypergeometric probability measure, this is its notation, on the set of n-particle configurations on this lattice. So the definition is as follows. Again, we have some normalization constant. Again, we have some product of some functions on the lattice. And some analog of the Vandermonde raised to power beta, but it is not exactly the Vandermonde, some analog. What is this analog? It is given by this formula. And it is actually a Q analog of this expression or of this discrete version on Z. And this function has this form. These are my infinite Pohammer symbols. And it is a QT analog of the previous expressions. And note that there are these shifts, which are necessary for the large n limit. And the parameter should be such that the weight should be non-negative, because we are dealing with probability measures, and the normalization is possible. So the conditions on the parameters are as follows. There are essentially two variants of sufficient conditions on these parameters, which guarantee that my construction is well defined. For all n, there is a principal series. Principal series means that alpha is conjugated to beta, and they are complex number, but not real. And a similar condition for gamma and delta is some inequality, which is needed for normalization. And then all the weights of the configurations are strictly positive. Next, there is a degenerate series. This means that we have these conditions for alpha and beta. They are now real, positive and negative. And gamma and delta, the conditions are the same. And then the measure is concentrated on the configurations which are contained in the so-called truncated lattice. Truncated means that the nodes are subject to these inequalities. So we have a picture like this. The configurations are contained in some interval of the lattice. But because they can concentrate near zero, they can be arbitrarily large. And the formula knows why this happens, because due to this condition, this product automatically vanishes for all x outside this interval. Now, the next step is to consider the set of particle configurations such that they are infinite now. They are bounded away from plus minus infinity, so any configuration is contained in certain interval, but it depends, its size depends on the configurations. Bounded away from plus minus infinity. And they should be tau sparse. So note that the pre-limit object of particle configurations are countable, but the space of infinite particle configurations has the power of continuum. And actually, there is a natural topology on this space, which makes it a totally disconnected topological space. Now I can state the result, which is the main result of my talk. It is as follows. So we fix a quadruple of parameters, which are in the print.
May I ask you a question, Grisha?
Yes, of course.
So you said that when tau is bigger than 1, then X should be sparse. But yet you said that it fits in a finite segment, right?
What fits in the finite segment?
The configuration fits in the finite, it's always in a finite segment. It is.
So I would like only to say that in the case of an infinite particle configuration, the particle does not accumulate to plus or minus infinity. They can accumulate only to 0 and not to plus or minus infinity. The configurations are bounded.
Okay.
Okay.
I see.
Well, so I assume as before this condition relating the t parameter to the q parameter for simplicity only. And the claim is that then there exists a limit of my hypergeometric probability measures. And the limit is a probability measure which lives on this space, on this topological space of infinite configurations on my lattice. So in other words, there exists a limit probability measure which determines a particle ensemble on the two-sided lattice with infinitely many particles which are allowed to accumulate to 0. So here 0 plays in certain sense the role of infinity. And I repeat that a similar claim holds in fact for any t without any restrictions. But the picture, the description becomes more involved. This is the result of these two papers. So now let me discuss the special, some distinguished case of tau equal to 1, which means that the two parameters q and t are the same. This in the algebraic combinatorics of Macdonald polynomials, this means that Macdonald polynomials becomes simply the Schur polynomials. So this is a truly distinguished case, the simplest two. So in this case, one can say much more. So assume q is equal to t, then the limit ensemble given by this limit measure is determinantal. This means that its correlation functions, I will define what are correlation functions, can be given by an explicit expression of which has a determinantal form, the correlation function number n. What is this? This is the probability that if you have given position x1, x2, and so on, xn, this is the probability to find particles at these prescribed positions. The configuration is random, so one can speak about the probability to see this position occupied. This is the correlation functions, and in such a situation, the totality of correlation functions for n equal to 1, 2, and so on determine the whole picture uniquely. So this is a complete set of invariants of our object. And in this case, we have a determinantal expression, just a determinant of an n by n matrix. And this matrix is a certain kernel, a matrix or a kernel on our lattice, which does not depend on n. And this kernel next, it admits an explicit expression, which in random matrix theory, this is called integrable kernels. So a kernel is a function of two variables, and in this case, it is expressed in terms of two functions of one variable of such a type. And these are certain functions which can be expressed explicitly through a Q hypergeometric function, which is a Q analog of a Gauss hypergeometric functions. And because the correlation functions are computable explicitly, one can say that the model with Q equal T is exactly solvable. The next result is that the limit measure is diffuse. Diffuse means that there is no atoms. The prelimit measure are purely atomic because they live on countable space. But the limit object is a diffuse measure, like, say, Lebesgue measure, which means that any individual configuration has measure 0. The next topic I want to discuss is degeneration. Degeneration of my picture to the discrete picture on the lattice Z, which I defined in the very beginning. So recall that we started with lattice Z and then proceeded to this two-sided Q lattice. And I already tried to note that the formulas in these two cases are similar. And moreover, it turns out that for each fixed n, our ensemble on the Q lattice can be degenerated to the ensemble on the lattice Z. To see this, assume for simplicity that these additional parameters are plus minus 1. So my lattice is just consists of these numbers or these numbers, where m is an integer. In this case, we have a natural bijection between Z and the positive part of this lattice. Simply to L, which is an integer, we assign Q raised to L, which is X in my notation. And likewise, in this case, we have a bijection between n particle configuration on Z and n particle configurations on the positive part of my Q lattice, which is given by this simple form. Next, fix a quadruple of parameters from the principal series, which corresponds to the case of the Z lattice, and assume that my new parameters are related to these old parameters by these formulas. And I want to consider the limit regime in which Q approaches 1. And then the Q lattice becomes more and more dense. And the theorem is as follows. In this limit regime, the random configurations on my Q lattice, which are governed by this measure, tend to concentrate near the point 1. In particular, this means that they tend to run away from the negative part of the lattice. And more precisely, fix an arbitrary small epsilon and consider the total mass of the set of configurations which are contained in a small but fixed interval around the point 1, where I here. Then it turns out that as Q goes to 1, this total mass is in the limit becomes 1. So all configurations tend to accumulate near the point 1. And moreover, for any configurations on the lattice Z, we have this limit, which means that we have a degeneration of my Q picture to the picture on the lattice Z. Here is some point. Here is some comment. So what I would like to emphasize, that in this limit regime, as Q goes to 1, the negative part of the Q lattice becomes negligible because the configurations tend to avoid the negative values. But however, in the framework of my approach, it's impossible to build a reasonable Q version of discrete beta ensembles only on the positive part. The two-sided lattice seems to be absolutely necessary. So it would be interesting to find a representation theoretic interpretation of this construction, at least for this distinguished case. A natural suggestion, because this is some kind of Q deformation, would be to work with representations of the quantized universal enveloping algebra. But I don't see how to reconcile this algebra with the two-sided lattice. So the phenomenon here is that if you want to quantize or find some Q version of the discrete picture of the Z, we need some duplication of a lattice. And there are some deep reasons why it's necessary. But it turns out that in the degeneration procedure, in the process of degeneration, this additional part of a lattice disappears. So this is one more topic I would like to discuss, a complement already. It's about some orthogonal system of symmetric function in the algebra of symmetric functions. So let me recall some very classical definitions. So what are orthogonal polynomials? So we have an algebra of polynomials. You have the distinguished basis of monomials. And you assume that we have some probability measure on the real line. Then if measure is sufficiently good, we can consider the space of L2 space with respect to this measure, and it contains the algebra of polynomials if a measure is sufficiently good. And then we can orthogonalize this system of monomials. And the result, orthogonalize. And the result, we obtain some systems of orthogonal polynomials. We can assume that plus lower degree terms, orthogonal polynomials. Let's now consider the algebra of symmetric polynomials in n variables. And we can embed it into the algebra of bounded functions, say of good functions, if measure is good, on the space of n-particle configurations on the real line, or maybe on some subset of the real line. So we have this embedding into algebra of functions on the real line. And assume that we have some measure, some probability measure on the space of configurations. And in good situation, we can embed the algebra of symmetric polynomials into the L2 space of the space of configurations with respect to this measure. And let's take here the basis of Macdonald polynomials. Macdonald's polynomials. And in some situations, one can find, again, orthogonal polynomials. One can orthogonalize the Macdonald polynomials. Macdonald's polynomials depends on the Young diagrams or partition. This is my notation for partitions of length less or equal to n. So the Macdonald polynomials play the role of monomials. And we want to orthogonalize them with respect to this measure. Which means that but here there is some difficulty which arises because the set of partitions is not ordered in the same sense as is ordered the set of positive integers. Let me show now the beautiful picture of the hierarchy of Q hypergeometric polynomials in one variables. This is taken from a lecture of Tom Kornwinder. So the polynomials are Q hypergeometric because they can be expressed in terms of Q hypergeometric functions. At the top, we have the Askew-Wilson and Q-Raka polynomials. And please look at this picture. At the second level, we have the so-called big Q Jacobi polynomials, which are a certain Q deformation of a classical orthogonal polynomial. And it turns out that there are symmetric polynomial analogs, I mean, and variate symmetric polynomials, which are n-variate analogs of these big Q Jacobi polynomials, as well as these ones, the n-variate analogs are called Kornwinder polynomials. And there are also n-variate analogs of Q-Raka polynomials as well. There is a big theory about them. So the topic I want to discuss now is that is there an analog of hypergeometric polynomials in the algebra of symmetric functions? And it turns out that at least some elements of the Q-ASCII scheme, this is and hierarchy, these arrows are, these arrows are some degeneration. So, for instance, Q-Raka polynomials can be degenerated to big Jacobi polynomials and so on. So a very rich picture. So first of all, at least some elements of this scheme admits analog for n-variate symmetric polynomials, and it turns out that they also admit some analogs in the algebra of symmetric functions. So this picture, at least some part of this picture can be lifted to the level of symmetric functions. This is the topic this is the second. So in more, at least in more detail. So we consider first the big Q-Jacobi polynomials, symmetric polynomials. So to do this, we focus on the degenerate series of parameters. I recall that alpha and beta are U, gamma, delta are subject to this condition, and we take a truncated Q-lattice. This is the configurations are contained in some fixed interval. I denote this truncated lattice by this symbol. So we consider again the set of n-particle configurations on this lattice. And again, I assume that the configurations are sparse. Can we consider the algebra of symmetric polynomials in n variables over the real numbers? And there is a natural embedding of this algebra into the algebra of bounded functions. This is possible because we consider the truncated lattice. We simply substitute these points as arguments of symmetric polynomials. And recall that we have defined some measure on this space. And using this embedding, we can realize this algebra of polynomials as a dense subspace of a Hilbert space, L2, with respect to this measure, and consider the induced scalar product in the algebra of symmetric functions. And there is a result by Stockman. So let lambda range of a set of partitions of length at most n. This is my notation for the Macdonald polynomials, which are indexed by lambda. And it turns out that there exists a basis in the algebra of symmetric polynomials. This is my notation, which with the top degree homogeneous component, the Macdonald polynomial, some lower degree terms, and they are orthogonal with respect to the inner product given by my hypergeometric measure. And these polynomials are called the n-variate symmetric big Q-Jacobi polynomials. And in the simplest case, these are classical objects. These are big Q-Jacobi polynomials discovered by Andrews and Askew. And what happens in the n-variate case? It turns out these polynomials, which obtained by Stockman, actually by degenerating procedure from Korn-Winder polynomials. So consider the expansion of these big Q-Jacobi polynomials with n variables in the basis of Macdonald polynomials. And it turns out that this expansion can be written as follows. These are Macdonald polynomials, these are my big Q-Jacobi polynomials, and these are the coefficients. And this coefficient, it depends on lambda and mu, mu is here. It depends on my parameters, but it does not depend on n. What depends on n is this expression. This is some combinatorial quantities, some of Q-Polymer type, but they do not depend on alpha, beta, gamma, and delta. So all the dependence on n is concentrated in these expressions. And I call this expansion almost stable just because the dependence is localized in this fraction. the proof is not easy, and it relies on some results, result by Eric Reins, and on which it relies on the theory of interpolation, Macdonald polynomials, which was developed by Okunikov, Knop, and Sakiev. So this is a long story. Now, what about the analog in the algebra of symmetric functions? This is my notation for all partitions, or the same as Young diagrams. This is the algebra of symmetric functions. And again, we can realize the algebra of symmetric functions as a certain algebra of bounded functions on the set. Okay. So here we have symmetric polynomials with n variables, and they become functions on particle configurations with n particles. And likewise, we have an embedding of the algebra of symmetric functions with infinitely many variables as bounded functions on the set of configurations with infinitely many particles. Just substitute the arguments, the points of my configuration into arguments of a symmetric function. So we can regard the algebra of symmetric functions as a certain algebra of bounded functions on a certain totally disconnected topological space, which is the space of infinite configurations. And this terms, the point is, as n goes to infinity, this terms goes to 1. So in this picture, this terms goes to 1. And this means that as n goes to infinity, the n variate big Q Jacobi polynomials converge in a certain quite natural sense to some symmetric functions, which is, this is my notation, it depends on Q and T and this quadruple of parameters, and only the pi coefficients survive here. So these are some new symmetric functions, and this is their expansion in the basis of Macdonald symmetric functions. And I call these functions the big Q Jacobi symmetric functions. And we regard them as bounded functions on the set on the space of infinite particle configurations. And by Stockman theorem, the pre-limit measure are the orthogonality measures of the n-variate big orthogonal polynomials. And the next result is an analog in the context of symmetric functions. So the result is as follows. So the limit measure, which lives on the space of infinite configurations, is my limit measure, is the orthogonality measure for these symmetric functions. That is, the big Q Jacobi symmetric functions form an orthogonal basis in the Hilbert space L2 on my space with respect to these measures. So actually, this is a particular case of the main result in the case of the truncated lattice. And so I would like finally just to make the remark that this theorem is somehow related to some general idea of constructing analogues of various systems of classical orthogonal polynomials, but in the algebra of symmetric functions. There are some other results in these directions. My joint work with Cuenca, and there we show that a certain part of the Q ASCII scheme that I showed you can be lifted to the algebra of symmetric functions in some different form, but more or less in the similar spirit. The very idea of lifting and variate analysis of orthogonal polynomials in the algebra of symmetric functions is present in earlier papers by Trans, by Sergei Fesilov, and de Rosier et Holmes. Well, so let me stop at this moment. Thank you.
Okay, thank you very much. Are there any questions?
So can you show again what are the new extra parameters of the limiting families that you were saying in the very beginning?
The parameters?
You said that there are extra parameters that you see in the limit, which were so the limiting object has more parameters than the initial discrete system. That is what you were saying. Some
additional parameters are z, w, z prime, w prime in the discrete case, and alpha, beta, gamma, delta in the Q case. These are the additional parameters. Additional with respect to, I mean, the additional, say, in comparison with the Dyson pictures. Or if we are looking at the limit of unitary representations, so let me sorry. So here, I would like to say that in this picture, in the representation theoretic picture, we want to take the limit of some natural representations which are realized on the L2 space, on the compact symmetric space, on the compact symmetric space, yes. In this picture, we do not see any additional parameters, but they appears after in some construction.
Okay. All right. I think we have time for one more question.
Yeah, I want to ask, what is the main idea of going from orthogonal polynomials to symmetric function?
The main idea?
Yes, just to repeat this.
So the main idea is that it is possible to extend the theory, the classical theory of orthogonal polynomials, first to the n-variate case, and next to the case of infinitely many variables. So we can construct some infinite variate analogs of classical orthogonal polynomials. I don't know if this is an answer to your question. Non-triviality in such extensions is related to the fact that the homogeneous components do not have dimension 1. So direct application of a Gram-Schmidt orthogonalization, the possibility to apply the Gram-Schmidt orthogonalization process is not evident at all. So this is some miracle that one can orthogonalize the Macdonald polynomials with respect to some measure. It's not evident from the very beginning.
Okay, well, let's us thank Professor Olshanski again. Thank you very much. Okay, so we're done with talks for today, and the buses for the banquet should be outside. And for those of you who want to stay at BIMSA, there will be a bus at 19:30 that will go through the hotels.